Hello, everybody. What we're going to be looking at here in today's lesson is talking about matrices and their inverses. Now, everything in math, we're able to generate an inverse of some kind. And in this particular course, we've seen inverses a few different ways. We've seen algebraically how to produce an inverse. We've seen graphically that inverses are reflected over the linear parent function, y is equal to x. And we've also seen that if I multiply inverses together, they produce the number 1. Well, the number 1 as a matrix isn't so much a number because it's a matrix. It's a collection of things. But there is an equivalent of what the number 1 is as a matrix, and it's called an identity matrix. Because generally speaking, anything in math says that if I did something that produced a 1, that would be considered an identity. And so what we're going to be looking at is, well, how is that identity used? What does it mean? Is it really actually kind of like a 1? Okay. And at some points we're going to be looking at how we can generate inverses, and we could show that if I multiply two matrix inverses to each other, I would get an identity matrix like this. But uh, an identity matrix at its most basic level is a square matrix, meaning it has the same number of rows as it does columns, and the diagonal entries of the square matrix are 1s, and every other entry in the matrix is a 0. So what we see here is an identity matrix of a 3 by 3. So an identity for a 2 by 2 matrix would have 1, 1, 0, 0, where the diagonal entries are 1 and everything else is 0. So that's what an identity of a 2 by 2 matrix would look like. And if 4 by 4 or 5 by 5 or whatever is everything is a 0 except for that uh, diagonal line going down. So what we're going to be looking at here is we're going to look at uh, matrix multiplication, understanding what we have as far as matrix being equal to each other are concerned. What we're trying to show is that kind of generic matrix ABCD that we have, it should be equal to the square identity matrix of the 2 by 2 that's just to the right of it. Now, understanding that for matrices to be equal to each other, they have to be the same size, and every part of every element of one matrix has to match exactly to every element of the second matrix. So what we see up at the top, where we say that ABCD being equal to the identity matrix on the right, well, we would say that those matrices are conditionally true as long as A equals 1, B equals 0, C equals 0, and D equals 0. So the way that we're going to demonstrate this is very much like the product sum approach of multiplying two matrices together. So the statement that we have at the bottom says, okay, take the matrix 9, 7, 5, and 4 and multiply it to that arbitrary matrix ABCD and show that it's going to equal itself, essentially. And the only way that it could do it is if ABCD is actually an identity matrix. Now, we're going to take the same type of approach of multiplying these values together like we would using the product sum approach, but we're not going to kind of keep it in its own brackets as a matrix. And I'll kind of explain why here in a moment. So again, just to, not because it's super necessary, if you understand what we did in our lesson over multiplying matrices, you're going to understand what we're going to do here. Okay, so I'm going to say the first row multiplied to the first column that's where the product sum approach of multiplying two matrices come into play, but it's going to be equal to the first element here of the solution that's been provided to us. So the way that we're going to kind of look at this is I'm going to say 9 A plus the next number, negative 7 times C, will be equal to a 9. Okay? And that would, everything as far as like firsts are concerned, that's how we're doing the matrix multiplication, but it's also saying equal to the 9 that's in the first element of what we have on the right there, the equal to part. So now we're going to, again, the color coding may not be necessary depending on your level of understanding from our matrix multiplication lesson. But now we're going to say, take the first row and multiply it to the second column here. And to finish out what would be kind of like the first row of our product is we're going to say it's going to be equal to this. Now, because we're multiplying two matrices that are 2 by 2s together, the product should also be a 2 by 2. So that's why everything is a square 2 by 2 matrix here. So looking at this, again, we'll take the first number of the row, 9, times the first element of the column, which is in this case is a B, and I'm going to say plus a negative 7 again. And if you just want to write a minus 7, that's fine. And times D, and it's going to be equal to the negative 7 of the first row of our second column of our answer that's on there on the right. And now we'll do the same thing with the bottom row. Okay, so we'll do away with the color coding at this point, and we'll just say negative 5 multiplied by the A plus the 4 multiplied by the C. And at this point, you can kind of see that top to bottom matching of the A's and the C's the same way that we did when we were looking at matrix multiplication. And that should equal to the bottom left, the negative 5 entry of our matrix on the right. We got one more element here that we have to fill in, and one more kind of equation that would give us essentially a 2 by 2 matrix. So again, we'll say negative 5 multiplied by the B of the second column there, and plus the 4 multiplied by the D, and that would equal to the last element of the matrix on the right, which is a 4. So essentially, what we have here written out in blue, those 4 equations, essentially is what produces a 2 by 2 matrix. Now, like I said, I'm not going to write this out as where I'm putting everything in brackets, because I'm not really going to look at this as a strict matrix multiplication. We're just using the idea, the process, to show ultimately that that arbitrary matrix ABCD is really an identity matrix. And I can't do that unless I really look at these as the equations that they are. So we're going to look at these as a system of 2 equations and solve for the variables A, B, C, and D the way that we would normally solve a system of equations. Now, personally, looking at the equations there, let's see, I think, no, I don't want a green on a green background. That would be silly. Let's do kind of a darker hue here. I think that will work okay. Pardon me. So here, what we're going to do is let's solve these systems. Now, looking at the system on the left, the one that has the A's and the C's, looking overall at the numbers, I think the 4 and the 7 are going to be easier to get rid of than the 9 and the 5. I mean, simply because overall they're just smaller numbers. So I'm going to multiply the first equation here by a 4, and I'll multiply the second equation here by a 7, and this, we'll see what we get. So the 9 and the 4 times the 9 gives me 36a. 4 times the negative 7 will give me a negative 28c equals a 36. And now we'll multiply through with the 7. So 7 times negative 5 is a negative 35a, negative 35a. The 7 and the 4 will give me a positive 28c, and that was the idea. We want to cancel out the c's. And 7 times negative 5 is a negative 35. And when we combine these here, uh, the 36 minus the 35 will give me 1a, and the c is canceled out, which was the idea, and 36 minus 35 is 1. And so here, if we're showing that, yeah, a is in fact equal to 1. So now I'm going to take that 1 and stick it into one of the other equations to figure out what c is. So I'm going to kind of just put it into, I don't know, let's put it into the second equation here. So if I say negative 5 times 1 plus 4c to be equal to negative 5, and let's figure out what c is. So negative 5 times 1 is negative 5 plus 4c equals negative 5. So if I move the negative 5 over through addition, I'm actually going to wind up with 4c to be equal to 0. So dividing 0 by 4 does give me 0. So yeah, we are showing that, yes, c is in fact a 0. So far 2 for 2. Okay, so now let's take a look, and I don't know, maybe we should pick a different color here for this. Something that I haven't used. Let's just do black. Okay, so now we're going to look at these two equations. Again, we're going to overall just pick a value to eliminate. And again, overall, generally speaking, the 7 and the 4 are smaller than the 9 and the 5. So I'm going to kind of do the same thing here. I'm going to multiply the top equation by a 4 and the bottom equation by a 7. And see what we wind up with. So here I'm going to get a 36b minus a 28d to be equal to a negative 28. And multiply the second equation by the 7, so the 7 and the negative 5 give me a negative 35b, and then a positive 28d, which is what we wanted. We want to cancel out the d. And the 7 times 4 gives me a 28. So combine, and we wind up with b equaling 0, which matches exactly what this which is matching exactly what this arbitrary matrix should be if it is indeed equal to the identity matrix. So now that I know that b is 0, I'm going to take it and stick it into any of the two equations. I'm going to stick it into the second equation again overall because the numbers are smaller than the first equation. So now I'm going to say negative 5 times 0 plus 4d to be equal to 4. Well, that canceled, so I have 4d is equal to 4, and if I divide both sides by 4 to get d by itself, I get the 1, so this is equal to 1. So yes, this would be the process, this would be the work that we would go through to show that in this case, the arbitrary matrix ABCD in this case actually is an identity matrix, so it is ABCD, the arbitrary matrix, is equal to the identity, and this is the work that justifies it. So moving on from looking at that identity idea, remember a little bit about inverses. Now this is something that if you want to pause the video and write it down, by all means go for it, but essentially just remember if inverses exist and I multiply them together, they should equal 1. So that means if I multiply a matrix and its inverse, it should produce an identity matrix. And same idea here. That's what the bottom statement is saying. Now the only thing that you really need here, I think, is the notation. Remember, this is just how we show what a matrix is, and anything to the -1 power is really the notation in all of math to show that it's an inverse of something. So that's what the inverse notation looks like. So here's kind of a mathy explanation of what that last slide showed you. Basically, n by n says it's a square matrix because it has the same number of rows and columns. So what it's telling you here is that it doesn't matter. This is the one time that the order really isn't going to matter when I multiply, because normally if I multiply matrices, the order that I multiply them doesn't always produce the same thing. In fact, most of the time it doesn't. That's what we talked about in our multiplying matrices lesson. But in this case, if I multiply something by 1, it really shouldn't change the outcome. So if I multiply a matrix and its inverse together, I should get its identity, which is effectively a matrix version of 1. Or if I multiply the inverse by the matrix, again, I should get a 1. So, or an identity of a matrix. So that's what that statement is telling you. Now, the title of the video is matrix inverses. So let's talk about how we actually find an inverse of a matrix. Now, what we're going to be looking at really are square matrices. That's what we can really find the inverse of. And the thing is that, first of all, not every square matrix has an inverse. That would, what we would call, be considered a singular matrix. If I have a matrix a square matrix that I cannot produce a an identity for, that is known as a singular matrix. Now, the way I determine if a matrix has an inverse at all, which most of them do, not all of them, but most of them do, we look at something known as a determinant. Now, the notation that we're seeing here, where it says det of A, this is saying the determinant of matrix A. Now, a determinant, don't ask me why we actually called it a determinant. Nobody, I wasn't around at the time for them to bother asking my input, but a determinant essentially is a scalar value, meaning it's something that I take and multiply it to the overall matrix to produce something. And that's exactly what at its most basic level, that's what a determinant is. It's really just a scalar number that I multiply to a square matrix to get something else. All right. And even though here it says we'll talk more about determinants in the next section, well, we see exactly what a determinant is on our very first example. So looking here, what we see, okay, we have another kind of arbitrary matrix. What we're saying, if matrix A is this, A, B, C, D, then its inverse, the way I find it, is by saying 1 over A times D minus B times C. That's our scalar. And it's being multiplied to, well, we just kind of rearranged the numbers of that arbitrary matrix. The D and the A traded places, and B and C stayed where they were, but we changed the signs of the numbers. Now, this right here, this A times D minus B times C, this is how I find the determinant of a 2 by 2 matrix. It's kind of like a formula. Now, we can actually expand on that to be any other sized matrix. In fact, I can show you how to do it with a 3 by 3 or a 4 by 4, but it does, there's just more numbers involved. It gets longer, slightly more complicated. But essentially, if I take these numbers in that order, if I say whatever this A value is multiplied by whatever this D value is, and I subtract whatever this times this is, that is considered the determinant. Well, the way I use the determinant is I actually take the inverse of the determinant. That's really what this expression is here. This is the inverse of the determinant. If I use that and I multiply it to this rearranged arbitrary matrix, that is how we produce the inverse of a 2 by 2 function. Now, 2 by 2 matrix. 2 by 2 square matrices, those are by far the simplest square matrix that we're going to be finding the inverse of. Finding the inverse of a 3 by 3 square matrix, even though it's only one row and column larger, the complexity of it really does go up quite a bit. So we're not going to really be doing a whole lot of stuff with 3 by 3 inverses, but here let's take a look and see, okay, well, can we find the inverse of this square matrix? And absolutely, it's really not that hard. Okay, so again, what we're going to say, this is just kind of the general rule. It's kind of like a formula. The inverse of the matrix is found by taking the reciprocal of the determinant, which is AD minus BC, and multiplying it to that rearranged thing where I say D and A trade places and B and C stay where they are, but their signs change. Okay, so here, well, let's see what we would get here. Okay, so just plug the numbers in that you see in your formula. And so I'm going to say 1 over. Okay, well, let me change where that is because I know I'm going to need a little bit of space for that denominator. Okay, so I'm going to slide it down just a bit. The inverse is equal to 1 over the determinant. So here, this is, you know, what is in the A position. This is what's in the B position, C position, and D position. So that's how I'm going to substitute my numbers into the equation on the left. So A times D is going to give me 3 times 2 minus B, which is a -1, times D, which is a 4. And we're going to multiply that to the wonky rearranged matrix where A and D trade places. So the 3 is in the A spot and the D is in the 2 spot. So this becomes 2 here and a 3 here. Now the B and the C stay exactly where they're supposed to, but the signs change. So B in the given matrix A is a -1. So now I change the sign, it becomes a +1, and the C, the 4, becomes a -4 in my wonky rearranged one. All right, so now what we're going to do, we have to simplify that fraction essentially, because that becomes the scalar value that gets multiplied to the matrix. So if you simplify the fraction, 1 divided by all of those values, 3 times 2 minus -1 times 4 gives me 1 over 10. And that is the value that gets multiplied to the 2, the 1, the -4, and the 3 of the overall rearranged matrix. And whatever those values are, that is the inverse of our matrix that we see here. So here I'm going to say 1/10 of 2, or 1/10 times 2. That's going to simplify to be 1 over 5. And 1/10 times 1 is just 1 over 10. Now, again, if the fractions work out to be a nice simple decimal, go for it, write the decimal, but otherwise leave it as fraction. So -4 over 10 really is going to just simplify to be -2/5, and 1/10 times 3 is just 3 over 10. So this is the inverse of the given matrix that we started off with. And then I'm not going to take the time to do it, particularly because of the fractions, but if we multiply our answer to what we started with, well, we would have an identity matrix left over. Now here is, you know, things are going to get a little bit wonky as far as the amount of work that we have to show here, because what we're trying to show is that take A times B and show that it'll produce an identity, and also rearrange the order and say B times A and show that it'll produce an identity. And what that will prove is that matrix B is going to be the inverse of matrix A, or vice versa, because this is about the only time that you should see two matrices, if I multiply them in a different order, producing the same thing. In fact, the same thing that they're producing is an identity matrix. Okay, so let's start with the A times B. Now, they're both 2 by 2 matrices, so I know I can multiply them together, and the product should be 2 by 2. So let's say, let's do A times B first here on the left and see what we get. So multiplying the row, using your row column product sum approach, I'm going to say negative 2 times 5.5 plus negative 6 times negative 2. Okay, so that would give me the first element of my first row. And then I'm going to take the same row, negative 2 times the second column, 3 plus the negative 6 times the negative 1. And that will give us our first. Oh, I made that second bracket way bigger than I think I needed to. Okay, and now we'll do the next row. Okay, so we'll take the 4 and 11 and multiply it to the 2 columns of matrix B, and so we'll say 4 times 3 plus the 11 times the oh, nope, I'm not paying attention again. Just back up. Stop screaming at your computer or your phone. So the 4 times the 5.5, there we go. See, the top and bottom thing is what told me I made a mistake. Because the 5.5 should have been the same thing in the second row. So now we'll say plus 11, and that will be multiplied by negative 2. And next row, or last portion of this product sum thing, we'll say 4 again multiplied by the 3 plus the 11 multiplied by the negative 1. So if you multiply all that stuff together, what you are going to get, negative 2 times 5.5 is 13, and 12, or I'm sorry, it's 11, negative 11, and negative 6 times negative 2 is a positive 12, and negative 11 plus 12 is a 1. And this would give you a 0, and this would give you a 0, and this would give you a 1. Type them into your calculator and double check me. And we have shown that A times B is equal to an identity. So now we'll do the same thing. Let me pick a slightly brighter color here than black. And let's do B times A. So B times A. So we'll do this same thing. Again, they're 2 by 2s, so we're more than capable of doing it. Now, in this case, because of the fact that on the screen, they're not written in the same order, if you want to write the two matrices down in the proper order of B times A so you can kind of see it, or maybe I'll just kind of put A here so we can see what's going to be multiplied here. So negative 2, negative 6, 4, and 11. So here's matrix A, so we can, keep things left to right the way they have been doing. So let's go here. So I'm going to say 5.5 multiplied by negative 2 plus 3 multiplied by 4. And then we'll do the next column of matrix A. And so I'll say 5.5 times negative 6 plus 3 times 11. And I hope that doesn't get cut off. And so now we'll do the same thing with the second row. So we'll say negative 2 times negative 2 plus negative 1 times a 4. And then we'll say second row to the second column, we'll say negative 2 times negative 6 and plus negative 1 times 11. And multiply those through again. So 5.5 times negative 2, that's negative 11. And 3 times 4 is 12 and combine those together, and I get a 1. And again, just double check me on the calculator, and this will be a 0, a 1. I'm sorry, not a 1, a 0 and a 1. So we do have an identity matrix in both cases. So this is one of the rare things when the order in which I multiplied my two matrices actually produced the same thing. Now, normally that doesn't happen, but that is the idea. Oh, and we're not going to get into this stuff here, so I'll just go back. So that is kind of the idea of how you find an inverse of a matrix. First of all is to take the inverse of what is known as the determinant and multiplied it by that funky rearranged matrix. And then finally, the fact that identity matrices, if I multiply inverses to each other, I will get an identity, and I can show that an identity really is in fact the matrix equivalent of 1, because if I multiply something by an identity, I get the same thing back. So that's what we were kind of covering in this lesson. Please make sure any questions or thoughts that you want to address to me in class or in tutoring, please get them written down and bring them to me at your earliest convenience. And again, as always, guys, thanks for watching, and we'll see you in class soon.